Yes. Hi, my name is May, and today I'm going to talk about a new experimental constraint on the reaction of oxygen-16 proton alpha and its role in Type Ia supernovae. Type Ia supernovae are known to reproduce most of iron group elements in the universe. However, some intermediate mass elements, such as the new silicon and sulfur, were observed in the spectra of Type Ia supernovae. Such intermediate mass elements are produced during the oxygen explosive stage, where the high temperature will allow the nucleus to overcome the high column barrier of the oxygen, and by fusing oxygens, we will have some silicon particles and other intermediate elements by capturing alpha particles during this stage. And capturing alpha particles will allow to create more heavier intermediate elements such as argon and calcium. So if the environment has many alpha particles, this means we will have more heavier elements such as calcium. But if the alpha particles are few, then the resulted elements will be towards the lower mass elements like sulfur. And it was proved that the ratio of calcium to sulfur is proportional to the alpha particle in the environment. And here where the reaction of oxygen-16 plays an important role. This reaction of 16 oxygen with a proton can create more alpha particles. So the oxygen will capture the proton to create alpha particle, which will enhance will increase the alpha particle inside the environment. This means it will create more heavier intermediate elements. But this reaction depends on the proton particles. So it needs a high proton abundances, and this is available in the low metallicity progenitors. Because in the low metallicity progenitors, we will have fewer neutrons that will not be enough to neutralize all the protons, and then we will have enough proton to initiate this reaction. While in the high metallicity progenitors, the neutrons will neutralize the protons, and this reaction will not be effective enough. And this can show that we can, and it was proved that we can use the ratio between calcium and sulfur as a footprint or indicator to the metallicity of the progenitor of Type Ia supernovae. Because in the low metallicity, we will expect to see a heavier intermediate elements, and if the lower intermediate elements is observed, this means it's related to the high metallicity progenitor. So it depends on the way of consumption of oxygen-16 consumption, and yet the models could not reproduce the observed calcium to sulfur ratio across different metallicities when they used the standard rates of oxygen-16 proton alpha and oxygen-16 fusion with carbon. And to fix this issue, there were two studies that used the observational data to constrain the rates and to make the observational data more agreement with the model's calculations. The first suggestion was in 2017 by reducing the rate of oxygen-16 with carbon by a factor of 0.1. The other suggestion is increasing the oxygen-16 proton alpha reaction by a factor of 7. And both of these suggestions were made using the observational data. And here we are examining the possibility to increase the reaction of oxygen-16 by a factor of 7. The variable rates for this reaction are in the libraries. We have Wigner and Starlib. Starlib has a statistical model, used statistical model to reproduce the rate, and had a factor of 10 uncertainty. And we have CF88 that is used in most models. And this gray area is the suggestion of increasing the CF88 by a factor of 7. And when we looked at the data, we found the cross-section data, we found some disagreement between the data. So we did a new experimental measurement on this cross-section, so we can deduce a new reaction rate. The experiment was done using multi-sampling ionization chamber of the music. And the new cross-section here, this is our new cross-section that was shown lower than other experimental data. And by using the new cross-sectional measurements, we were able to calculate a new reaction rate with the constrained uncertainty. And you can see that compared to CF88, the rate cannot be enhanced by a factor of 7. And it's almost by a factor of barely 2 of CF88. So in summary, we discussed the role of oxygen-16 in Type Ia Supernovae nucleosynthesis and the challenge on the rate. And we proved that this rate cannot be enhanced by a factor of 7 of CF88 rate. And this might indicate that we need to do more evaluation of the other reaction of oxygen-16 with carbon and try to refine the Type Ia Supernovae models. Thank you.